Okay, good afternoon, everyone. So this is Physical Science 118, Astronomy. My name is Daniel Lor, the faculty of the Department of Meteorology. Ano to ba? So last meeting, we discussed about Module 2, Lesson 2.1, which is orbits and gravity. So we discussed Kepler's laws of planetary motion. So we have three: Kepler's law of planetary motion, and after that we also discussed Newton's law of motion. So now put tayo three laws of motion by Newton, and we discussed some sample problems that might appear in your midterm exam. We also have some computations involving mass, the relationship between mass, volume, and density. And lastly, we discuss Newton's universal law of gravitation. So for this afternoon, I will be discussing to you the continuation of lesson 2.1, which is the coverage of our midterm exam. So let me share my screen. So the first problem we have to solve this afternoon is this one. So what is the average distance from the Sun of the planet Saturn with an orbital period of 84 years? So when we talk about average distance, um, since we already know that a planet is revolving around a star, or in our case, in the case of the solar system, we are revolving around the sun. That our path or our orbit is not a circle. So we are orbiting in an ellipse. So therefore, our distance, so for example, this is your sun. So our distance from that sun changes depending on whether we are, because we are in because our path is an ellipse. So therefore, we are traveling, or there are parts, or there are times when we are at the farthest part of the sun, which is the aphelion, and the parts of our orbit when we are nearest the sun, that is the perihelion. So for sa kaninga problem, we are asked to solve for the average distance. So that average distance can be also equated to the semi-major axis, A. So kana siya nga A is the one being stated in the third law of Kepler, or Kepler's third law, which is stated as the square of your orbital period is equal to the cube of your semi-major axis, or in our case, this is your average distance, or this can be equated as your average distance from the sun. So for your midterm exam, you have to follow the procedure, or the correct procedure in answering problem solving. That is, you first have to write the given, followed by what are required, and lastly, the solution. So for this problem, the only given here is your orbital period P, which is equal to 84 years. Again, based on our previous discussion, if your orbital period is years, okay ra nga dili nimo isuwat ang word na years, because automatically your average distance, or your A, which is your semi-major axis, is equal to, or ang iyang unit is automatically in AU. Again, AU or 1 AU is the average distance of the Earth from the Sun, which is approximately equal to 150 million kilometers. In astronomy, again, it is more convenient to use the unit AU because we can visualize, the distances, comparing it to the distance or the average distance of the Earth to the Sun, which is equivalent to 1 AU. So what is being asked here is A, the average distance. And for your solution, you have to write all of the equations or equation that you will be using. So in our case, we have P squared is equal to A cubed. What is asked is A, so we can rewrite this as A is equal to the cube root by getting the cube root of both sides of the equation, cube root of P squared. So this is equal to the cube root of P, which is 84 squared. Step by step, you can just write what is the cube, what is the square of 84? 7,056, and getting the cube root of 7,056, that is 19.18. Now you as what we have discussed during our last discussion, no need na nga ibutang ang unit nga years diri sa ato because automatically if your orbital period is in years, your A is already in AU. So this 19.8 is already in AU. So put your final answer in a box. So that will be your final answer. Any comments, any questions regarding our problem? If you have questions, please write them in the comment section below. Before we proceed to our next example, please hit the like and subscribe button. And to receive notification from my YouTube channel, please click the bell, the notification bell. The next question we will be discussing this afternoon is this one. Suppose astronomers find an Earth-like planet that is twice the size of the Earth. So specifically, he emphasized that the size here refers to the radius of that Earth-like planet compared to the Earth. So twice kuno. So what must be the mass of this planet Earth, planet-like Earth, or Earth-like planet, such that the gravitational force F gravity at the surface would be identical to that of the Earth? Again, we have to write what are given. Required before you write your solution. So from our problem, mura magwalay given nga gihatag. Sakto? Ato sa nang i-skip ha. So for the required, what is required is the mass of the Earth-like planet. So ato na siyang butangan og EL. For our solution, we can use here the law because it is kanang state naman gid diri sa problem, the gravitational force, and based sa atong discussion, last discussion, the gravitational force or Fg, we can also write F sub gravity is equal to the universal gravitational constant divided by the mass, the product of the two masses divided by r squared, wherein your r squared is the distance between the center of gravity between those two objects. So for example, you have here two objects. So the r is the distance between the center of their gravity. So that would be your distance r. Again, from the center of gravity. Dili ang kaning distance dire. No? So, dili na mao. So, from the problem, giingon nga the force of gravity for both of those planets, the planet Earth and the Earth-like planet, should be the same gravitational force or identical gravitational force. So if the gravitational force for the planet Earth is G, okay, let's see that the gravitational force of Earth, E, is equal to G times the mass 1. In this case, our mass 1 is the mass of, nag-record lang ko. Oh, nag-record ko. Sorry. So, kaniyang mass 1, it could be anything that is on top of the surface of the Earth. No, times mass 2, which is the mass of the Earth, divided by r squared. Okay, this is the radius of the Earth. So, ato na butang radius of the Earth here. However, given that the radius of the Earth-like planet or radius EL is equal to twice the radius of the planet Earth. So, man siyang atong kanang given, no? Mura may given sa atong problem. And even though we are not, or we don't know, or dili given diri ang radius sa Earth, we can still solve this problem. So the gravitational force in the Earth-like planet, EL, is equal to G times the mass of an object on top of the Earth-like planet times the mass of the Earth-like object sa EL divided by the radius of the Earth-like planet squared. Since these two should be equal, therefore, kaning nasa right side sa ilang equation should also be equal. So we can rewrite them as G, kaning first, kaning siya. G, mass of that person or an object in the surface times mass of the Earth divided by R, E squared is equal to G times mass of the object in the surface of the Earth-like planet times the mass of the Earth-like planet divided by REI squared. However, we know that REI squared is 2 times the radius of the Earth. So therefore, we can rewrite this equation, but before we rewrite, we can already cancel out the variables or the factors G and the first mass. Therefore, the mass of the Earth divided by the radius of the Earth squared is equal to the mass of the Earth-like planet divided by, to ato ni siyang i-substitute, 2 radius of the Earth squared. So most of the students, dili sila masayo. So dili nila i-appeal og square si 2. Ang ilarang i-square si RE. Again, kinahanglan i-square nimo ang tibuok nga 2RE because REI is equal to 2RE. Distributive property of exponent. So ato distributing squared. So we can write that equation to M sub E over R sub E squared is equal to m sub el divided by 4, because 2 squared is 4, re squared. So we can cancel the factor re squared. So mo siya akong gingon a while ago that even though we don't know the radius or the radius of the Earth is not given in the problem, we can just proceed with the solution. So multiplying both sides of the equation by 4, therefore, the mass of the Earth-like planet is just equal to 4 times the mass of the Earth. Put your final answer in a box and submit to me your solution. You can also state here that the mass of the Earth-like planet is 4 times the mass of the Earth, so that their gravitational force will be the same or will be identical. Any questions? If you have questions, please comment down below. So reviewing Kepler's third law of motion, our p squared, which is in years, is equal to a cube, which is in astronomical unit, meaning the larger orbits, A, have longer orbits period, and the average orbital speeds are slower for planets with larger orbits. However, Newton found out that there is a flaw, murag na ay sayop sa third law of Kepler's third law. And after deriving gravitational orbital motion from the laws of motion, from the law of gravity, and a little quite bit of calculus, Newton arrived ani nga revision of Kepler's third law. So iyang gi-apply ni Newton dire ang katong gravitational law, ang Newton's gravitational law. And inserted this factor m sub 1 plus m sub 2. So makita nato ang similar, ang difference sa duha ka equation. And Newton also showed that this equation may be expressed in physical units because ang kaniyang equation, our P is in what? This is in years, and our A here is in astronomical unit. But we can also rewrite that in this form, wherein your P is in seconds, your A is in meters, and your mass is in kilograms. We also use the G, or the universal, the universal gravitational constant. Okay. So how can we understand this relation between the period of the orbit, the mean distance, and sum of masses? So just as we have discussed during our discussion last week, we can recall that the acceleration of a planet in its orbit around the sun depends upon the mass of the sun and the inverse square of the planet's distance from the sun. So therefore, the acceleration of a more distant planet due to the force of gravity between it and the sun must be smaller than the acceleration of a planet near the sun. So as a result, a more distant planet must orbit the sun at a lower average orbital speed. So mas hinay ang movement sa distant planet. So kaning mga planet nga Mars, Jupiter, Saturn, Neptune, Uranus, mas hinay ang ilang orbital speed. And slower orbital speed in a larger orbit mean that its orbital period must be longer. So sa atong module 3, we will discuss the orbital periods of the different planets in the solar system. So makita nato nga mas magtika layo sila sa sun, mas magtika dako ang ilang orbital period. And mas magtika gamay ang ilang orbital speed. Mas hinay sila mulihok compared sa mga planets nga duol sa sun. No? So, sa solar system, pinakapaspas mo tuyok sa sun, si Mercury, followed by Venus, then followed by the Earth. So it is important for us to know that the force of gravity between the sun and a planet can be larger than between the sun and the Earth. Yet, the planet's acceleration can be either larger if it is closer to the sun or smaller than the Earth's acceleration in its orbit around the sun. This is because the force depends upon the product of both masses and the square of the distance between them. That is Kepler's second law, whereas the planet's acceleration depends on just the mass of the sun and the square of the distance between the sun and planet. So for example, the force between Jupiter and the sun is 11.7 times that between the Earth and the sun. And yet, Jupiter's orbital acceleration is a factor of 27 smaller than the Earth because Jupiter lies 5.2 times further away from the sun than the Earth. And 5.2 times 5.2 is equal to 27. So in order for us to further explore on this relationship, we have to review our discussion in Kepler's second law. So going back to the third law of Kepler, note that the relationship between the orbital period and the average separation between the masses actually depends upon the sum of the two masses, M1 and M2, orbiting the common center of mass. That this relationship should involve mass should make some sense given what we already know about the relationship between force, mass, and acceleration, and that the force of gravity itself depends upon masses of the bodies involved. Okay. Note that for the case of our solar system's planets orbiting the sun, the sum of the masses correction to Kepler's third law. So muna siyang na-observe ni Newton. M1 plus M2 measured in units of our sun's mass amount to a factor of at most 1.000955, which is for the sun and Jupiter masses, it will be equal to 1 plus 1 over 1047. Because the mass of the sun is equal to 1.989 times 10 to the 30 kilogram, and the mass of the planet Jupiter is equal to 1.898 times 10 to the 27th power kilogram. So although Kepler has forgotten this factor here, M1 and M2, but because this formula is referred to the mass of the sun, therefore, okay ra gihapon, sakto ra gihapon to ang formula ni Kepler. So we will compute for the percentage of, if we will divide these two values, we will arrive at 0.0955%. So gamay ra kaayo ang difference nila. Gamay ra kaayo ang effect sa planets nga ga-orbit sa sun. So the masses of those two planets, if we will add, is just equal to 1 plus 1 over 1047. So gamay ra kaayo ang contribution sa mass sa Jupiter to the sun, or this is the maximum, no, kay ang Jupiter man ang pinakabug-at nga planet revolving around the sun, or kung ang planet nga naay gravity around the sun. So therefore Kepler had it nearly right. So murag sakto gid si Kepler in his description of the orbits of the objects revolving around the sun. On the other hand, this mass correction term is very important. So it is advisable that sa atong pag-compute, we use this equation, kaning modified or revised equation by Newton. This again, this mass correction term is important, especially this is example, no, significantly different from a factor of 1. Okay, kung kani siya at ni siyang i-add, that is around 1. That is 1.000955. So gamay ra kaayo ang difference to the factor of 1. So other cases involve the orbits of two masses when one of them is not our sun. So examples are solving the gravity between the Earth and the Moon, solving the gravity between stars, so star to star, or even planet to its satellite, or our planet to the satellite, or planet to the moon, to their moon. So our question would be, if the star that Earth orbited were more massive than our sun, Earth's acceleration would be what? So you can pause the video and try to answer this question. So the correct answer here is greater. So from Newton's law of motion, force is equal to mass times acceleration. Because the force will be higher, therefore our acceleration here will also be higher. So the correct answer here is greater. Next question. If the star that Earth orbited were more massive than our sun, Earth's orbital speed would be what? You can pause the video and try to analyze. So the correct answer here is, duha ra may atong choices. It could be faster or slower because we are talking about speed here. So the correct answer is faster. Why? So based on Newton's law of general based on Newton's universal law of gravitation. No? So ganito yung atong formula. So we have F gravity is equal to G. G is constant. We have M1, M2 divided by R squared. So if the Earth, so kung atong ni siyang i-increase, ang mass sa Sun, therefore, ang atong gravitational force will be also increased. And based sa second law of Kepler, based sa second law of Kepler, sa ganito yung second law of Kepler, Kepler's second law states that the straight line joining a planet and the Sun sweeps out equal area and space in equal interval of time. So therefore, kung mas dako ang force, mas dako sad ang iyang speed, which will result to a slower orbital period. So the orbital period will be slower, or this will be shorter. Ay mas paspas man ang speed or ang speed sa Earth around this massive Sun. So this is what I discussed earlier. In Kepler's third law, mass 1 and mass 2 measured in units of our Sun's mass amounts to a factor of at most 1.000955, given that because the mass of the Sun plus the mass of Jupiter is equal to 1 plus 1 over 1047. So mura siya unity. Thus, Kepler had it nearly right in his description of the orbits of the objects around our Sun. However, again, this mass correction term is very important, significantly different from a factor of 1 for all other cases involving the orbits of two masses when one of them is not our Sun. So, ang given akong example a while ago are the orbits between the Earth and the Moon, the orbit between stars, and the orbit between even planet and any satellite. So, does the mass of the planet have a significant impact upon its orbital period or orbital speed about some star or in our case, about the sun. So given that planets are, by definition, almost always much less massive, di ba? Ganiha, atong gi-example, at most, ang pinakadako nga mass around the sun is the planet Jupiter. Pero gamay ra gihapon ang impact, no, almost one ra gihapon ang ilang sum sa ilang masses. So the practical answer here is no. However, if you will be asked if there are any effect, yes, so there is always the gravitational effect, even kung unsa kagamay ang mass sa usa ka object. Well, yes, of course, there will be an effect since the force of gravity does consider the masses of these paired objects. So look at Newton's corrected version again. This is the corrected version of the Newton's law, the Kepler's third law. So it does indeed include the masses of both the objects. So what if Jupiter with its mass of 318 Earths orbited the Sun at Earth's location rather than Earth, ignoring the presence of nearby planets because kabalo man ta nga dako kaayo si Jupiter, therefore dako kayo siya comparatively sa Earth. So kung atong i-replace si Earth with Jupiter, so maigog gud niya si Mercury and Venus. So again, what if Jupiter will replace the Earth in its orbit? So si Jupiter atong ibutang sa Earth's orbit. So what will happen? So well, the mass correction factor would be 1.000955 instead of that of between the Earth and the Sun, which is 1.00003. So kung Sun and Earth, that would be 1.000 pila ka 0, 5, 1, 2, 3, 4, 5, 3. So that is for the Earth. So in that case, the orbital period of Jupiter in Earth's orbit would be a tiny, tiny amount shorter, which is around 1.000476. So the difference would be 1.000476. Gamay ra gihapon ang ilang difference. Okay? So for questions and clarifications, you may email me, kabalo naman mo sa akong email ad, or you may comment down below. So this is the last, so these are my references. I will be sending this to you also, my PowerPoint presentation, so that nagihapon mag-serve as your reference, no, during your review for our midterm exam. Okay, so that's all for our discussion this afternoon. Thank you and see you next week. God bless your exam. Bye-bye.